There's a promotion for the monthly that we as a lot of use our meditation. So I can have maybe there's a and we just
Meeting is being recorded. Sorry.
Okay, welcome everyone. I hope audience can hear us. If you can't, please type in the chat and we'll try to fix it. But otherwise, it's a great pleasure to introduce Longfei Shenguan, who is an assistant professor at the University of Pittsburgh with research interest in mobile health, wireless networks, and IoT. And thanks for being here. We look forward to this talk.
Sure. Thanks, Cecilia. Thanks for your nice introduction. Hey, everyone. My great pleasure to be here sharing some of my past and ongoing research on building wearable devices. And I'm going to talk about some of our ongoing efforts on building wearable devices, which actually pioneered by Cecilia. So, one second. Why my pointer doesn't work? 1 second. No worries. Yeah. So let me start with a quote from Tim Cook. So Apple CEO, everyone know him, right? So Tim once said, after a few years, if you look asking what is Apple's the biggest contribution, biggest achievement to the whole society, it's actually on the health domain. That's actually a very bold vision, right? Over the past decades, Apple is known for its sleeker smartphones, laptops, has sort of quietly transforming into one of the most influential, one of the most successful health tech players. The most important part here is that you can see this breakthroughs, it didn't happen through the clinical great machines setup. It happens something as everyday as a smartwatch, something millions of people are wearing every day on their wrist. That's actually make a fundamental shift. Mobile health or the health, it never only happens in clinical setup. It's becoming wearable, It's becoming data-driven. It's almost everywhere. So let's zoom in for a moment. This is what this shift has been looked like in the past decades, right? So in early 2015, Apple Watch start tracking our fitness, start tracking our heart rate. Simple, but very groundbreaking features. Later on, 2020, it start tracking our sleep, give us a whole cycle sleep quality monitoring. And recently, Apple start tracking our health, like hearing health, which is also fundamental biomarkers to most of us, right? So this timeline isn't just like a product roadmap, right? It's actually a map of ambition, like step by step. You can see Apple is trying to build a health agent, stay in our ears, stay in our wrist, stay in our pocket, trying to provide us around the clock monitoring. That's actually a clear signal. Apple is betting big on the health domain, right? But the problem is this progress reaching all of us? So let's not look at this harsh reality. So look at this fancy starting like Apple Watch. It costs roughly like over 400, some special edition over $1,000. Well, that's actually the problem, right? This kind of health revolution, mobile, data-driven, and sensor-rich, it's more like designed for those people who can afford it, who can spend like over $400 to buy it. But for most of us, for most of the people living in the whole world, particularly those living in underserved communities, how come could they spend such amount of money to buy these health feature rich devices, wearable devices? Now let's paint another picture of the two worlds. As you can see in rural areas in United States, there's roughly 19% of people who have this smartwatch, who have the devices I introduced before. When it comes to the urban areas, this number jumps to 40%, over double the number, the percentage in the rural area. This gap is actually a wake-up call, right? So imagine a farmer living like rural areas, rural village, a worker like living in like, like bustling city, right? So accessing to these healthcare devices, health monitoring devices, shouldn't depend on where you live, right? It shouldn't depend on which zip code you have. Now let's cross the boundary, looking at the people living in different worlds. So Senegal, like the monthly salary income is around 360, but in United States, it jumps to over 4,400, over 10-fold more, right? So now thinking about if you are like citizen living in Dakar, which is a capital city of Senegal, an African country, and earning this amount of 360, looking for an Apple Watch, how come? How could you buy it? You're gonna spend your whole month's income. So such inequity not only happens on the system cost, it actually happens on the technology itself. So imagine there are 3 people wearing the Apple Watch monitoring their heart rate, like one from, for example, UK, the local UK has a sort of light skin. Someone like me come from Asia, we have a medium, skin tone. Some are Native American, someone like African American, dark skin. So the problem here is that the research studies show there's a bias. So essentially for people with dark skins, their like heart rate monitoring performance is not reliable compared to people in light skins. So why? Why this happens? Why the PPG sensor has a bias? We know PPG is actually shedding a light to our blood vein, right? And then detect this reflection signal to sort of monitoring your heart rate. The problem here is that for people in dark skins, they have more this kind of melanin. So this melanin gonna absorb light. So as a result, for people in dark skins, this melanin is gonna absorb more reflection signal, making your reflex signal way weaker than those reflected by people in light skins. So now, if we still believe, as Tim Cook said, the biggest legacy of Apple is on the health domain, we should ask, like, who gonna benefit from this legacy, right? So this question is actually at the core of my talk today. How could we build those unbiased, ultra low cost wearable devices, not only nice to have, but also like, everyone living every corner of the whole world need to have. So before we start, let's just imagine like when you are like stepping aboard a plane where, a flight attendant's gonna hand out a free earphone to you. So usually we just use it once, right? We may throw it away, leave it on the seat, or take it back, left on the drawer, never use it again. So think about every day, millions of these low-cost earphones are dropped off. Like, they becoming a serious problem, electronic waste. So now, what if we could turn this electronic waste into a feasible solution? What if we can like this electronic waste into something can monitor our health? Then this can not only solve the health equity, low cost issue, it can also solve this electronic, a big environmental issue. So we start looking to this problem since 2021. And on the high level, we believe this is feasible. Why? Because we know all our physiological activities, like beats, brain lung functions, they're gonna generate these vibrations, right? All these kind of vibrations gonna pass through our human body all the way up to the ear canal. So imagine now you're wearing the headphone, you can actually pick it up, right? Not only the music, but also these vital signs to monitor your heart rate. We know those signals are there. They are residing deeply inside your ear canal. But for most of the earphone we talk about here, like those we get from the airplane, those as a supplementary devices we got when we buy, for example, iPhone, when we buy a laptop, they give us a free earphone. They mostly do not have an ear. So how could signal? It's more like, there's a very beautiful music is playing, but no one is listening, right? So to solve this challenge, actually we're inspired by a physics principle have been taught since we are high school students or middle school students. We know the speaker was built to playing the sound, which can transform this electronic signal into the audio by using diaphragm, by using the voice coil, and the magnet, right? So the key here is the hardware is totally work in reverse way. So essentially, we know this diaphragm gonna transform all your audios into this electrical signal. which means that essentially repurposed it to capture your audio inside your ear canal, right? So this hardware reciprocity essentially gave us a chance to pick up these biomarkers, these vibrations, this crucial, like, audio signal already residing inside our ear canal. So as we embark on this journal, I want to use a few questions to guide us go through this technical roadmap. So first, imagine those vibrations are already there. The natural question to ask, do these minute vibrations provide you enough signal-to-noise ratio, SNR? Particularly, can we pick it up by using this repurposed speaker as a microphone? Then, if we could use this, repurposed speaker to pick up these vital signs, does this vital sign provide you the same quality of heart rate, breath as those dedicated medical grade devices? Last but not the least, how can we deal with the interference? How can we deal with the noise? If there are music playing, they are way higher, way stronger than the very weak biosignal captured from your canal. How can we handle it? So let me briefly show you how the signal looks like when you pick it up using a speaker as a microphone. For comparison, here I first plot the music when you pick it up, use the speaker as a microphone. You can see the power is roughly around 100 millivolts. Then when you're tapping the earphone, as shown in the middle figure, it's roughly give you around 2 to 4 millivolts, signal level, the amplitude. You can see on the very left figure, the heartbeat is so weak, it's sub millivolts. So essentially, see there are 200 times gap in their amplitude. So now if you are playing music, your heartbeat will totally overwhelmed by this strong interference, right? So back to 2021, we proposed a system called the Hi-Fi. So this is like a plug and playing module. It costs roughly a few dollars. When you plug in your earphone, we can start detecting your heartbeat. We do some signal processing. It's mainly on the circuit level to cancel this strong noise interference. So let me briefly go through how the Hi-Fi works. So I will ignore the digital signal processing part since most of you are pretty familiar. Low pass filter, high pass filter, and some base methods. So to noise interference from music, from other human speaking, we are using a circuit called the Wheatstone bridge. So Wheatstone bridge was originally designed for measuring the impedance of any given capacitor. So the Wheatstone bridge on high level have two bridges. The upper part, we call it upper bridge. It has two identical resistor, so their resistance are the same. On the lower part, you have one CX, which usually connect to the unknown capacitor. You want to measure their resistance, capacitance. And then C1 is a trim port. So the tricky part here is that the output VG can be 0 when both the upper bridge and the lower bridge are balanced. When I'm saying these are balanced, I'm saying these two resistors, the resistance are the same. So here, we're gonna tune the C1 trim port until the output of the VG is 0. In this case, we know the reading of C1 is actually reflects the resistance of CX, right? It's quite easy. It's a null circuit. So how I leverage this Wheatstone bridge to cancel the music interference. So let me briefly show you how it works. So in our system, what we do here is like we do replace C1 and CX with two like earphone transducer, because you come with a left earphone transducer and right earphone transducer. In the meantime, we're gonna replace the power source on the very left part with an audio input. As I mentioned, once this whole circuit, the wisdom bridge is balanced, no matter how you change the input within audio, the output of VG is always 0. So essentially, it means that if the bridge is balanced, no matter which kind of music you are playing, how you tune up, tune down your music, output of VG is gonna be 0. So when you're wearing this earphone, we know this vibration gonna propagate right to your ear canal. The tricky part here is that since this signal gonna broadcast or go through two different paths to the left and ear, usually like the path from the cardiac from your heart to the right ear is longer than the path to the left ear. So the impedance variation caused by the heartbeat to your left ear transducer and right ear transducer gonna be different, which means that this heartbeat gonna break actually the balance state of this wisdom bridge. Said differently, VG now have readings. And the reading of this VG actually reflects the heartbeat signal. So let me show you a brief demo how we leverage this to measure the hertz rate. So this is then like back to 2021, we are collaborating on this project. As you can see, when he wearing this earphone connect to this small like prototype, you can measure the hertz rate. And here is a let me show you again. Here is the ground truth hertz rate 84, 85, 86, right, from the pulse oximeter. And then like when we turn off, you can see, it switched too fast. Get here on the upper left, 86, this is actually the hertz rate we got. Quite close. I mean, if you want, right, you can do it. Put it on your puppy and start marrying him or his or her like hertz rates, right? So yeah. Oh, sorry, I forgot to play the audio video. It works. I mean, I'm not sure if it works for Catty, but I bet it should be. But Catty sometimes not like as friendly as dog, so it may take more effort. So now that we can measure the heart rate using this low-cost electronic waist earphones, so what else could we do? Because heart rate is important. It's one of the fundamental biomarker, right? We're just wondering, can we do more? Can we extend to other types of biomarkers for like health, around the clock health monitoring? So in early 2022, we started exploring heart sound. So can we like go beyond heart rate, start monitoring your heart sound? So heart sound not only reflects your how many beats per minute, it also show you more fine grains like S1, S2, sometimes with murmurs, and also sometimes with like S3 and even S4, which is really the symptoms of like cardiac issues. So heart sound, as I mentioned, is actually a very important biomarkers to assess your cardiac, functions, detecting those cardiovascular diseases. So to answer the question, so let's start looking at the earphone recordings we get from the head file. So as you can see, the signal quality although we can sort of leveraging autocorrelation to detect your heart rate, but the problem here is that you can see that's still very noisy, right? You can see roughly each heart cycle, but you can almost you cannot almost tell where is S1, where is S2, let alone those very weak murmurs. So how could we leverage this hardware, to extend it to the heart sound recording, heart sound recovery? So to answer this question, we take a step back, start revisiting all the signal propagation paths. We want to know where the problem comes from, why the signal is so weak. So we divide the signal propagation into 3 phases. The first phase is the embodied signal transmission, right? We know the heart sound gonna propagate through your canal from your chest to your canal. They're gonna suffer from attenuation. They're gonna suffering from reverberations, right? A lot of vibrations, multipath effect. So after the signal arriving at your ear canal, it's become pretty weak. Now, since we are using speaker as a microphone to pick up this heart sound, the problem here is that speaker was designed for signal playing, not for signal recording. So its energy transfer efficiency is extremely low, which means that when we use a speaker to pick up this heart sound, only a small portion of energy gonna be transformed into electrical signal. So in other words, now the picked up signal will be way weaker than before. So lastly, we know this heart sound signal, very weak, gonna go through your cables to your parent device, like a smartphone, like a laptop, right? So here's another problem, impedance mismatch. So earphones usually have roughly 20 ohm or not about 40 ohm resistance impedance. But for the smartphone, they have a higher impedance. They do have a lot of electronic components, right? For the laptops, for the lap PCs, you have way higher impedance. So according to the transmission line theory, when the impedance of one device and another are not fully matched, so when this signal goes from one medium to another, there's a lot of energy gonna be reflected back. So as a result, we know only another very small portion of energy gonna be detected, finally delivered to your parent device. So that's why back to the hi-fi detected signal is extremely weak. So if we want to recover, or if we want to keep the high quality heard sound, we have to figure out a way to solve these problems, either in the first embodied channel, or on the earphone interface, or in here, right? So let's briefly go over the 3 components again. We know for embodied channel, we cannot put an amplifier inside your body, right? So it's really hard to handle it, on the hardware. Then on the second part, earphone interface, since we want to recycle this electronic waste, we don't want to break. We don't want to rebuild something to recapture this heartbeats. Then we can almost do nothing here. Then we switch our focus to the last part, impedance mismatch. So if we can well match the impedance between the earphone and your parent device, we know we can guarantee most of the energy gonna be delivered to your smartphone or your parent device, right? So we start modeling this part using a very simple circuit. So here we use a Z to represent the impedance of your earphone. Delta Z is actually the impedance variation caused by your heartbeat. Here, the ZF is the impedance of the smartphone. So this diagram basically shows how this circuit looks like. So let's take a step back. We know ZE for now is not equal to ZS because the earphone's impedance is lower than the smartphone's impedance. As a result, most of the energy here gonna be reflected back when it transmits through this wired cable, right? Only a very big, small portion of energy gonna go through here, go through the internal electronics on your parent device. So what we do here is we build this ZP is a programmable impedance part. So our goal is trying to make sure ZP with the impedance of your earphone, the programmable impedance, and ZE is the impedance of your earphone. When you add them together, we want to make sure this value is similar or equivalent to the impedance of your smartphone. And this way, you can match their impedance so that most of the energy here, right, they're gonna be transmitted to your pairing device. Only very, very small amount of energy gonna be reflected back. So here I give you a high-level diagram of our hardware circuit. So on a high level, it has three components. The first part is this digital trim port. So why do we need a digital trim port? Because different earphones, different pairing device, they do have drastically different impedance, right? This is not a one-time offline calibration. You have to calibrate online. So that's why we need a programmable trim port. And our idea for the online impedance matching is also simple. We send an ultrasound using left earphone, and then recording this earphone, this ultrasound on the right ear. And then we tune the impedance until the SNR is maximized. In this way, you can match their impedance in a very fast way, right? You can definitely use a hertz rate or hertz sound to tune this impedance, but your heartbeat is quite slow, right? It's gonna take a lot of time to balance the impedance, to match the impedance. So the second part is this AC coupling. This is a basic, circuit design trying to block the slow varying DC offset. Usually it's gonna give you strong audible noise, which gonna contaminate your hertz sound recordings. The last part is amplifier, which is differentiable amplifier trying to amplify the detected hertz sound all on the circuit. The total cost, I think, is roughly $3 to $5 for now. So let me show you now how the signal looks like by using this new hardware. So we do plug in those wasted earphones to this new hardware prototype here, and we're trying to collect heartbeat signal using oscilloscope. And yeah, one thing I forgot to mention is since we know this hertz sound or this earable-based solution, they are insensitive to your skin tone, of course, right? So this is another fundamental benefit. I think the hertz sound looks way better, or heartbeat signal way clear than the signal we collected from the HeadFi platform. So the hardware component help us to best capture the hertz sound from the ear canal. But the problem we know there are also another two steps, right? Signal goes through your body, attenuates, and also due to this reverberation, some of these high frequency components, they get lost because signal on the high frequency, they suffer more from the attenuation than those low frequency part. So compared to the ground truth on the upper side, you can see the hertz sound recorded by our new hardware. We can record S1 and S2, but we lost some high frequency component, which is crucial for hertz sound reconstruction, hertz sound based diagnosis. So to make it a real useful tool for hertz sound recording, heart sound, like, based diagnosis, we have to do more. We have to handle this embodied reverberations, high frequency deafness. So we start looking into a software solution because, as I mentioned, you cannot put an amplifier inside your body, right? So we start, with the hardware gave us a pretty clear heart sound signal. And then we start the pre-processing and segmentation because we want to handle each heartbeat one by one. So on the pre-processing part, we're gonna first filter out those using a low pass filter to filter out those high frequency component alias, keep the S1, S2 energy more dominate. And also we leverage this amplitude-based outlier rejection method to sort of filter out those body motion artifacts. Sometimes they are strong spikes, right? After that, we also apply the Wiener filter, trying to handle the multipath, the echoes, the vibrations. So actually the Wiener filter is quite a strong tool, which have been demonstrates very useful in ECG-based cleaning and ECG-based pre-processing. We borrow this idea here. So after that, we're gonna segment it. So the boundary of the segmentation is quite important. So that's why we are also very carefully deal with the segmentation. Start with the envelope cortical correlation to find each roughly hertz cycle, and then go through the HMM, hidden Markov model, to model how this heartbeat changes, because different user, they may have slightly different heart rates, right? You cannot use a heart threshold to segment. So HMM is trying to model how your heartbeat changes. And even for a single user, we know your heart rate is not stable. Sometimes going up, sometimes going down, right? So after all this pre-processing segmentation, now you have each hertz cycle here, which have a clear S1 and S2 component. We start looking into how to recover the missing high frequency component. As I mentioned, this high frequency deafness coming from the reverberations, from the attenuation inside your human body. So we borrow encoder decoder architecture, trying to reconstruct your frequency, spectrogram of your heart sound. So input here is a spectrogram of the heart sound we collected after the pre-processing. It has a 6-layer encoder, 6-layer decoder, and the loss is just the L2 loss between your spectrogram. So after this spectrogram recovery process, you can see it gives you some fine-grained high frequency component compared to the plain heart sounds recorded pre-processed using our hardware. But the problem is we found when we're listening to this recovered heart sounds, sometimes you can hear some glitch. Sometimes you can hear some strong noise. So why? Because on the spectrum recovery step, we do not explicitly deal with the phase. So phase is actually very, very important here, because if you're not carefully deal with the phase, there'll be phase discontinuity, which is gonna cause this kind of group delay. So that's why if there's a sudden phase changing, it's gonna cause a glitch. So which gonna contaminate your heart sound. So that's why after the spectrogram recovery, we add another component to do the waveform refinement. So this is more like the time domain, signal recovery. It's still the same architecture, but here we are doing it on the time domain. So the spectrogram goes through the inverse STFT to gather time series data, and then we start the recovery their phase. We do use a time domain loss, L1 loss, to guide this whole training to make sure your recovery signal not only spectrum similar to each other, but also their phase is continuous, similar to the input. So now let me play some recovered heart sound from this hardware and software solution. So first, let me show you what we recovered. Sorry, maybe it's too weak. Can you hear it? No? Okay. Let me play it again. I don't know where the sound is gone, but yeah, it's quite similar to we have a lot of audio samples online. You can feel free to try it. So it's not we said, oh, it is similar to each other, then it is good, right? We have to talk to the cardiologist, right? They are the experts. So we actually take a user study. We invite 5 cardiologists to test it. So this is a blind testing. So essentially we mix 25 pieces of audio recovered by our algorithm, our system, shuffle it with another 25 ground truths. So the cardiologists are not aware of which this signal coming from, whether from the ground truth device, which is a stethoscope, digital stethoscope, or coming from our system. So you can ignore the absolute correctness ratio, but focusing more on the gap on each category. As you can see, the gap here is quite close to each other, which means that the cardiologist cannot tell which is from which. So essentially, they can achieve quite similar diagnosis accuracy on both our recovered heart sound and the ground truth. And most tricky part here is that for the murmurs for this category, we have even better correctness rather than the ground truth. So actually, we are trying to figure out why. So we talked to the cardiologist, and from their feedback, we feel actually our recovery algorithm gonna amplify the murmurs, because murmurs usually very weak, right? From the stethoscope, sometimes you may not be able to notice the murmurs, but our algorithm gonna amplify that component, which gives the cardiologist a strong signal. Oh, there are some murmurs, maybe something wrong with heart sound recordings. All right, now we are briefly touch upon heart rate onto heart sound. I want to briefly talk about we are currently working on is a positive velocity monitoring using this electronic wrist. So positive velocity is also another very important biomarkers. It actually reflects arterial stiffness, right? It's also related to hypertension and also aging. So in clinic science, it always working this way. You're lying down, we put a few devices on your neck, on your leg, or on your wrist. Then we measure the pulse, your heartbeat. So once you know the distance between these two measurement sites, then you can use a time difference to calculate the velocity, right? Very basic physics principle. As you can see here, you know the delta t, you detect these two peaks on two different sites. You can calculate the positive velocity. So in our system, we're trying to use 2 pairs of earphones to do that. So essentially, we have 1 pair of earbuds putting here, one on your neck, another pair of earphone on your wrist. Once you measure the distance between your wrist to your neck, and you detect this heartbeat, you can start calculate in the same way. So this figure briefly shows the setup. So this is a commercial earphone. This is a speaker sending an ultrasound. And then this is a line-in mic. So some of the earphones have the line-in mic for talking, right? So we use this line-in mic to detect these reflection audios. We are sending the ultrasound. So we know, when the blood goes through your, when the heartbeat goes through your blood vessel, your muscles gonna reform a little bit, right? So essentially, it's gonna generating a frequency shift on the Doppler domain. So essentially, we can use the Doppler effect to detect these heartbeats, and then get to know their time delay, right? This is actually measured. The blue line is measured on the neck, and the black line is measured on the wrist. So essentially, you can calculate the time difference between these two peaks, and you estimate the positive velocity. So to me, like I do believe research is not only about pushing the boundary of our knowledge. It should be also about pushing more people to the boundary of knowledge. So in early this year, we actually fly to Senegal, St. Louis, start testing, start to getting feedback from their local village, from their medical schools to see whether our earbud devices are helpful and what other pain point do they have. So we actually talk to their medical school. We are actually to go to their village, talk to their local nurse. So this demo briefly show our testing with their some college students in St. Louis. It's Justin Berger University with our collaborator. So we do this real-time demo and show how our signal recover their heartbeat, heart sound. So as you can see, from the heartbeat, noisy because the ambient noise is very strong there. So we have to sort of using on-ear earphones to detect recording. You can see she's smiling, which means she's quite happy with her sound when she started listening to it. So I will briefly talk about some takeaways, some findings we have here. So first of all, we found earbud not only can serve as a personal health monitoring device. Actually, based on the feedback, we found earbud can also serve as the pre-screening tool to them. Because we found when we go to their village, we found actually they do not have any pre-screening tool. Whenever the villagers come to the nurse, they can just describing what's going wrong, and how I feel about, but there's nothing the nurse can do. Either recommend them to go to see the clinics, which is really far away from the village, or just taking some local medicine, traditional medicines they have. So they can actually use this earbud device. They are excited about that. They feel they can use this device to sort of monitor, to do the pre-screening. The second part is not only the pre-screening tool, they are also lacking of real nurse to do the diagnosis. So we went to 3 villages, only 2 of them have the nurse. So they also mentioned that usually there's a nurse, maybe 1 nurse per village or less. And sometimes they just travel around to this village today, to another next time. So they are really lacking of nurse to do the diagnosis. So it's really challenging, particularly in the rain season in Senegal, because their transportation system is really bad. So they have to take some local medicine without very effective diagnosis. And even told us if it works, then it works. If it's not, it is what it is, unfortunately. So the most impressive memory I had here is a meta lesson I learned. So this picture briefly shows a clinic which was built through the President's Malaria Initiative. So essentially, United States, give them a bunch of money building these clinics. But these clinics never been used as clinics. Why? They don't have pre-screening too. They don't even have any medicines. So that's actually the problem, right? So you have the money, but you never use it in a correct way. You have the building there, you take photo, and you have the news we have Senegal, we have this country, but no one benefits from there. So after the visit, we feel we are so excited. We feel, oh, we get good feedback. We should work more. We should do something real benefit to their local community. So currently, in collaboration with our collaborators in Senegal, we are applying the IRB there. And in the meantime, we are building new hardware prototypes because in the system I introduced before, they are all signal offloading paradigm, right? So you have to offload signal processing to for example, your laptops for your smartphone, which is quite expensive, right? So you never think about everyone in rural Senegal gonna have a smartphone to process it, right? So notice that we are not our new types of hardwares. We want to do everything on board and also minimize the cost. $5 or $10, send it for free. In the meantime, we are trying to deploy new testing experiments, new testing sites. So we have been talking with them, have the weekly meeting talking about this deployment scenario. Currently, we have a plan in mind to on their hospitals, primarily for verifying the clinical effectiveness. And then 3 on their local village, trying to grab the data, store locally, and our collaborators gonna visit the villages every few weeks, grab the data, and then do further analysis. So yeah, that's pretty much about my talk today. I just want to show you a beautiful picture we took from Senegal, from my student, Hongbo, at Pompaga. So it's a very beautiful sunrise. So with that, I want to wrap up my talk. Happy to take any questions. Thank you.
Yeah. For the online audience, please put your questions in the chat if you want. In the meanwhile, if there are any questions from the audience here, Jake.
For the head phi, you have the Wheatstone Bridge.
I'm sorry?
For the head phi, you have the Wheatstone Bridge.
Yes.
And if I wanted R2 that are perfectly matched for some tolerance,
yeah,
you have the music leaks into the signal they trying to target.
Also mean like the signal leakage?
But if R1 and R2, you can't get them the same.
Okay.
Tolerance, for example, would that cause some kind of leak or error?
So right. So even your 2 bridge are not perfectly matched, which means that VG always have a recording, right? But the tricky part here is that you are looking at the variations, not the absolute value, right? So even VG, the auto VG is not 0 without the heartbeat. But now when there's a heartbeat, the signal gonna varies over time. So essentially, even this is not perfectly matched, you can still detect the heartbeat signal. Yeah.
Adam, I hope I got the order right.
Sure.
Also about the Wheatstone Bridge. Why did
It's the right order.
you use that and not just the sort of the differential amplifier?
Why do I use null circuit, you mean? Or
Why would you use the Wheatstone Bridge
okay.
and not just the differential amplifier?
Right. So as I mentioned, the Wheatstone Bridge was primarily used for canceling the impact of the input audio. So as you can see, when we replace the voltage supplier to the Wheatstone Bridge with the audio input, no matter which kind of song you are playing, which kind of audio you are playing, it will not change the impedance. It will not change the status of your Wheatstone Bridge. If you just use a differentiable amplifier, it can only just amplify your input signal, right? It cannot cancel.
Your case on those lines, that is.
Oh, I see your point. I see your point. Right. So then that actually depends on which kind of music you are playing. If it's a stereo music, these 2 music will be different. You cannot cancel it. Right. Yeah. But that's a good point. Yeah. If you are just playing non-stereo, mono music, it will definitely work. But stereo, no. Yeah.
So I also have another question about the Wheatstone.
Oh, sure.
So in the videos you've shown the speakers always in both ears. So I wonder how it works that it's not canceling out the heart rate signal because you're using both speakers to balance the circuit.
Right.
So why is it not canceling out the heart rate if it would be visible on both ears, right?
You mean when you say it will not cancel the hardware, you mean it will not cancel the heartbeat signal? Is that what you think?
Because the heart rate affects both speakers, right?
Right.
So why is it
Ah.
not canceled out by using stereo?
Got you. The thing is like, for the heartbeat signal, when it propagates to the left ear and right ear, the path length is different, which means that the heartbeat when arriving at two ear canal, like they are in different amplitude, right? When you cancel or when you do the difference between these two signal, they are still remaining, gonna reflect your heartbeat signal, right? It's like the asymmetry between these two ear respect to your like cardiac activities.
Thanks.
Sure.
Yes, okay. then
Yeah,
I'll take.
I'm Yang from Nokia.
Oh, hey, yeah.
Yeah, I have a question regarding to, since you are using speaker as a microphone, do you
Right.
think about using the speaker as well, using a single speaker transmit something and using the same speaker to pick up something that reflect back as you did in APG?
APG, right. We also think about that. So one thing about the APG is like our personal experience is like, I mean, it's not that reliable because, like we are essentially profile how your ear canal structure changes over time due to the heartbeat, right? So this kind of minor change, first of all, is really hard to pick unless you're sending the ultrasound, right? So essentially, like, ultrasounds, they are more sensitive to the minor variation of your structure, right? The second thing is like, it's very susceptible to body motion or like, when you knock your head or like swing your head, it can sort of break it. So I'll say for reliability, I do believe your solution in your mic to recording is more reliable, to be honest. Right. So yeah, I was briefly talking with Cecilia students. We are currently handling this, interference from body motions on APG, trying to leverage in multimodal solution to solve it. Because you have MU data, MU gonna reflect how your body moves, right? So this is one opportunity to handle it. Yeah.
We have
Sure.
2 questions online and you can read them there, but I'll read them aloud for the audience.
Sure.
If the signal recovery step is skipped, would the captured signal still retain fine-grained heart sound features? In other words, how important is the recovery step for preserving subtle acoustic details?
Sure. So let me explain in details. So first of all, like, as you can see from the other hardware signal detection enhancement, signal becomes pretty clear. But the thing is, you have sort of like, deafness on the high frequency component. Because like when the signal passes through your human body, the high frequency component of the heart sound, they're gonna suffer more from attenuation. And it's also due to reverberations, some of these parts gonna be totally messed up. So essentially we're using this fun, spectral recovery algorithm trying to reconstruct this missing part. So essentially it's quite important. I didn't get a chance to show you like how the sound looks like, but it's quite different. Yeah.
There's a follow-up question on new users. If the system would generalize to new users, the performance has been evaluated in 0-shot scenario.
Right. That's a very good point. So I cannot say it will definitely generate to everyone because we do not go through a very rigid clinical like testing, something like that. So what we do here is like we test on 30 users. And what we do is we are using the public data sets, train the model, trying to make it scale to different kinds of scenario. Yeah. So it's more like the best effort.
But you don't test on a user which you're trained.
Right. We don't. It's just like, it's more like
you do test on a user.
we do leave one out
Yes,
testing.
okay.
Yeah.
All right, I think we are coming up to the time. So thank you very much, audience here and online, and thank you to the speaker.
Sure, thank you.
Yeah, thanks.